So this is an explanation of how to do workshop 2. So let's start with problem 1. We want to take the solid obtained by revolving about the horizontal line y equals -1, the region bounded between these two lines. Which is a better color there. There we go. Okay, so let's just quickly draw what this looks like. This is our axis of revolution, y equals -1. Now the two lines that we see here, x minus y equals 0, let's focus on that one. That's just x equals y, or the line y equals x, so that's just going to be this line here. And x minus y equals -1, if we solve for y in terms of x, we just get y equals x plus 1, so that's going to be this line here. And we're doing this on the interval 0 to 2. Put in some tick marks there. So what we're talking about taking that region and revolving it about this line. So what we want to do is draw one representative cross-section is going to be a washer, and as we see, it's going to have a big radius and a small radius. So we know that the radius of the big circle, or like capital R, is going to be, it's the top line, so this is y equals x plus 1 there, and here we have y equals x, so this is going to be the top radius is going to be x plus 1. That's the vertical vertical height of a point on that circle, and that's going to be the distance between there and the axis of revolution is going to be x plus 1 minus -1, or x plus 2. And then the small radius, here we've got this point here has a height of x, and again we subtract -1, that gives us x plus 1. So what we know is that, I'm running out of space to do this, but oops, sorry. The we know that the area of this washer is going to be, don't know why that keeps happening, the area of the washer is going to be pi, do not understand why that keeps happening. It's going to be pi times x plus 2 squared minus x plus 1 squared. That's going to be the area, the cross-sectional area, but we're asked for the volume of one thin cross-section, so we have to actually, instead of just making this like a flat surface, we have to give it a little bit of thickness, and that's dx. So that is just going to be, keeps doing that. That's just going to be dx. Okay, so let me just write this up here. This is going to be pi x plus 2 squared minus x plus 1 squared dx, and that's the answer to this question. Okay, now let's go to question 2. Okay, so we have in question 2 is, if we scroll here, you'll see that I'm asking you to take this region, this green region, and revolve it about various lines, of which the first two are horizontal lines, and the second two are vertical lines, x equals -5 and x equals 10. And the significance here is that whether you use x or y depends on the combination of A, is the axis horizontal or vertical, and B, which method are you using, because in both cases they're switched. So in the case of a horizontal axis by the Diskwasher method, this is going to be a dx integral. Why? Because we have here is, if I call that y equals -3, we can see is that we're going to draw in washers that look like this, and the important point is that the washers are thick like that. In other words, they're thick in the x direction. So what we can do is we can see that we have a top curve and a bottom curve. So the volume is going to equal the integral. We can see the lowest and highest x values are 2 and 3, so that's going to be 2 to 3. And then pi, we're going to have the outer radius squared, that's going to be the top function in this case, minus the inner radius squared. So in the case of the outer radius, we can see that any point on this curve is going to have the form x ln x. So its y value is ln x. That means the distance to the x-axis is ln x, but we have to go a little bit further. We have to go down all the way down to plus 3. So this is going to be ln x plus 3 squared. And by the way, that plus 3 is not something that's being fed into the ln function by convention. This is just the natural log of x, and then whatever that is, plus 3. And then we subtract from that. Negative 1 minus negative 3 is just 2 squared. You didn't actually have to simplify this to get a correct answer. I'm just doing it. So, all right, so that's the Diskwasher method. Now, the shell method. The thing about the shells, I'm going to erase this now so that we can see what we're doing in the x direction. So the thing about shells is that shells, to revolve around a horizontal axis, keep that, keep that there, y equals negative 3. To revolve around a horizontal axis using shells, what we have shells that are on their side like that. So a couple of things to note. First of all, the thickness of each shell is vertical, so it's in the y direction. What that tells you is the entire problem has to be done in y. And the other thing to note here is that the height of the shell, or what I'm calling here the quote height, because it's really on its side, is going to be defined by the distance between this vertical line x equals 3 and this vertical line x equals 2, but only until you get to this point here, at which point the right, the right side of the region is x equals 3, but the left side of the region is this curve. The other thing to note, and there's a lot of other things to note here, is that because we have to do the problem entirely in y, we can't use ln x as the description of the curve. We have to solve for x in terms of y, which is going to be x equals e to the y. Okay. So, in other words, the same curve here, which is y equals ln x, can also be described as x equals e to the y. All right, now we're ready to write the expression. So the volume is going to equal the integral. Let's go up from the bottom. We start here at negative 1. So remember, we're doing this in the y direction, so we're not looking for the lowest and highest x values, we're looking for the lowest and highest y values. That's going to be negative 1. This line here is y equals ln 2. So this is going to be negative 1 up to a value of ln 2. And for a shell integral, we're going to do 2 pi. We need the distance from the outside of the shell, which is there, to the axis. So if this is some arbitrary point y, the distance to the axis is y plus 1. And then finally, we need the height of the shell, which is 3 minus 2, or I could have just written 1. And then finally a dy. But then we need to do the top part. The highest part of this region, when I say this region, I mean this little top part here where the left and right boundaries are different. And this is the important thing about switching the directions here. What you'll see is that the right side of this region is given by the line x equals 3, but the left side is given not by x equals 2, but rather by this curve. So still going to do integral sign. We're going to go from ln2 up to ln3. Why? Because the lowest part of this region we're now describing up here is ln2, and the highest part is at ln3. Picking an arbitrary value y in the middle of that region, we still see that it's different, that its distance to the axis of revolution can still be described as y plus 1. So that's going to be y plus 1. And now we have right minus left, which is 3 minus e to the y dy. So there we go. So that is the shell integral. All right, so I'm going to do the other ones a little faster. I'm just going to talk about what the difference is. So here we've got the line y equals 7. Back up. The line y equals 7 is, actually I can just draw it again. So that region looked kind of like this. That's ln2, ln3. So the line y equals 7 is like way up here. So a lot of things are going to be the same about this problem, and some of them are going to be different. The main issue is that it's now going to be this curve that's closer to the axis of revolution. So in the case of a washer integral, this curve is now going to be the inner radius, and this one is what's going to form the outer radius. In other words, when we revolve this around the x-axis, you can see that now it's going to look, I can't really draw the whole washer in, but it's going to look like that. So now it's this part that's on the bottom of the region that's going to form the outer radius. So what we write is v equals the integral, once again, 2 to 3, the lowest and highest x values in the region, and it's going to be pi times the inner radius squared, sorry, the outer radius squared. The distance from y equals 7 down to this line, y equals -1, is going to be 7 minus -1, or that's going to be 8 squared. And the distance from 7 to this line was y equals ln x, that's going to be 7 minus ln x squared dx. Okay, now, so let's do the shell integral. The shell integral is going to be very similar to what we had before. It's going to be -1 up to ln2 of 2 pi, just put this in. The vertical distance, the vertical height of the shell is still going to be 3 minus 2, and we're still doing this in the y direction, so dy. The only difference is that if this is y, then the distance between 7, sorry about that, between 7 and some arbitrary point y is the difference between 7 and this arbitrary value y is going to be 7 minus y. So we put in 7 minus y there, and then finally we're going to add in, we're going to add in the integral from ln2 to ln3 of 2 pi 7 minus y, and then this is going to be 3 minus e to the y dy. Okay. All right, so that's the answer to 2b2. All right, now let's do the x-axis. We're going to do vertical axes in C and D. So once again, the region looks like this. There's the region. I'm drawing it in kind of small. The line x equals -5, so that's x equals -5. So what changes here? By the Diskwasher method, what we want to do now is we want to stack washers this way. They're going to have to look like this. So they're thick in the dy direction, which means we have to do everything now in the dy direction. What we can see is that here, the inner radius is defined by this line, x equals 2, until you get up to this point, and then it's defined instead by the line x equals e to the y, like that. So by the Diskwasher method, this is going to be v equals the integral from -1 to ln2 of pi. We're going to do outer minus inner, so that's going to be 3 plus 5. That's the distance from this line x equals 3 out to the line x equals -5 squared, and then minus 2 plus 5. That's the distance from the line x equals 2 to the axis -5 squared dx. And then we have to add in the part that's above this line, y equals ln2. See the last drawing, and then that goes, of course, up to y equals ln3. So we're going to add in the integral from ln2 to ln3 of pi times 3 plus 5 squared minus e to the y plus 5 squared dy. Oops, I forgot that's actually a dy here. I make a big point of that. That when we do vertical axis when we're doing a vertical axis in using washers, that has to be a dy integral. And notice, by the way, that any time that I had an opportunity to write a variable, it's always a y. If you have a dy integral and there's an x anywhere in your integrand, you're just wrong. If you have a dx integral and there's a y anywhere in your integrand, you're just wrong. So remember that. If you do it, you're on a test, you've solved the problem and you're sure you've got it right, but your integral ends with dy and you have an x, just accept You got it wrong. You're getting a 0 for that. Back up and redo the problem the correct way. Okay, so let's do the shell method. Vertical axis with a vertical axis with the shell method is the easy method because we do that in the x direction. So this is going to be v equals the integral from 2 to 3, lowest and highest x values, 2 pi, and this is going to be from some arbitrary value x out to the axis is going to be a distance of the axis of x equals -5. That's going to be a distance of x plus 5. So that's the radius of the shell. And the height of the shells now, they're tall, so the shells look like that. So the height of the shell is just going to be ln x minus -1, or I can just simplify it a bit, say plus 1. Where is that? That's because the distance from this curve here to the bottom of the region is ln y minus -1 or plus 1. So there we go. So that is the answer there. All right, and now the only difference in this problem is we've got the same region, of course. The difference is we've got an axis that's way out here, x equals 10, which means we're going to really do the same thing, except it changes for the washer method, it changes which is the inner radius, which is the outer radius, and for the shell method, it means that the distance between here and here is going to be 10 minus x because we want to subtract larger minus smaller. So okay, so for the disk method, we have v equals the integral from -1 to ln2 of pi times, we have, let's see, we're going to do outer, which is 10 minus 2 squared, and then inner, which is 10 minus 3 squared, dy, plus the integral from ln2 to ln3 of pi times the outer, which is 10 minus e to the y. In other words, that's the distance from here to that curve. Remember, this curve is y equals ln x, or x equals e to the y. And then minus 10 minus 3. We have to square both of those. And dy. There we go. So that's the shell integral, and sorry, that's the washer integral, and the shell integral is going to be 2 to 3, 2 pi. It's going to be just like the previous one, except that the only thing we're changing is how we define the radius of the shell. That's going to be 10 minus x, ln x plus 1 dx. So that's the answer. Okay. So we have problem 2 done. This is a really important problem. This is exactly the kind of thing that you might be asked to do on a test. So you should really make sure that you do understand how all of these work and why the integrals are in a particular direction. Let me just write one thing out for you. Shell, actually, let's see. Diskwasher and shell. So let's write horizontal and vertical. We'll write sort of like a little table here. So diskwasher, if we have a horizontal axis with the diskwasher method, then this is going to be dx, and the shell method is going to be dy. If we have a vertical axis with the diskwasher method, then that's going to be dy, and a vertical axis with the shell method is dx. That's simply how it works. And ideally you shouldn't memorize this table. Ideally you should understand the geometry, but if anything, you can fall back on this table. This is how it has to work. Okay, so let's, oops, there we go. Okay, so now we want to just solve one more volume problem using the same region. So the base of the region from problem 2, cross sections perpendicular to the x-axis, are squares. So what we have that same region. I'll just draw it quickly, like that. And perpendicular to the x-axis means that we're looking at the the side of the squares are like that. That's perpendicular to the x-axis. And then they kind of grow out of the page. So what we do is we take the side of the square and we square it. So what we're getting is the lowest x value in the region is 2. The highest x value in the region is 3. The length of that side is just going to be ln x plus 1, and we square it. And if we make it a little bit thick in the x direction, you can sort of see these are squares that would be, I'm terrible at drawing these things. I'm probably just making it more confusing by drawing it, but they're growing out of the page like that. Okay, so that's the answer there. And if instead we change it so that we're looking at the cross sections are squares perpendicular to the y-axis, then once again we have this shape, which I'm drawing like worse and worse each time. And recall that we have ln2, ln3, and this line here was y equals -1. So we do kind of the same thing. It's like the side of the square is like that. It's the distance between left and right, but the definition of what the left part of the region is changes up here. So this is going to be v equals integral from -1 to ln2 of 3 minus 2 squared dy plus the integral from ln2 to ln3 of 3 minus e to the y squared dy. And there we go. Okay. Let us go on to the next problem. Consider the region bounded by y equals x squared on the interval 0, 2. So let's draw the region, and I'll show you why. One of these gives the volume described, and the other one does not. So the thing to recognize here is that the region looks basically like this. I want to draw this in a different color, actually. Not good. Okay. There's the line, and here's the parabola. Okay. So let's draw in the two parts of the region being described, because this is 1 and this is 2. So let's put in that. So I put these in two different colors, and sorry, I'm not very good at filling that in. This is not going well. Let's see. There we go. Okay. There we go. All right. So, all right, the yellow region is the part between x equals 0 and x equals 1, and the part that's between these two curves, between 1 and 2, is this sort of red or pink region. So I'll put it in the dot showing where they cross. So these curves cross here. So the important point is that if I were to revolve this around the x-axis like this, what I have here is I've got washers that look like this. So in this case, the line on the interval 0 to 1, the line is what's giving the outer radius of the washer. All right, so the interval 0 to 1, the line gives the outer radius of the washer, and the parabola, which is closer to the x-axis, is giving the inner radius. But once we go over here, what we now have is that the outer radius is given by the parabola and the inner radius is given by the line. So if I were to do this, if I were to do the integral from 0 to 2 of pi, let's say, x squared minus x squared squared, where I'm always subtracting the line minus the parabola, I would get a positive volume up to 1, but then look what happens. Once I cross over to 1, these values are bigger for x greater than 1, these values are bigger than these values, which means that I'm subtracting a small number minus a big number, and I'm getting negative numbers here. So what I would do is I would keep adding up positive volume here, but then once I got to this point, the integral would automatically start subtracting volume. So I wouldn't really get the volume of the solid obtained by revolving these two things, by revolving these two curves around the x-axis. Instead, what I'd get is the volume of the yellow part of the solid formed by the yellow part minus the solid formed by the red part. On the other hand, if I take that same region, let's just draw it quickly. If I take this same region like this, I'll just shade it in this way. So part of it is blue stripes, and the other part of it is green stripes. So in this drawing, if I do the integral that's shown here, then keep in mind that what happens is, yes, I'm still subtracting on the interval 0 to 1. I would still be subtracting a bigger number from a smaller number, but look what happens. I square it. So when I square the number, I get a positive number anyway. So when I take the squares, I'm adding a positive volume there, and then I'm still adding positive volume here. So the bottom line is that the second integral has a negative integrand on the interval 1 to 2, but the first integral has a positive integrand throughout the interval 0 to 2. So in the second case, we're always adding up positive volumes, whereas because of the nature of the solid, once we switch which curve is top and which is bottom, we also switch which one is inner and which one is outer. So we end up, for half the region, for half of the interval, we end up adding negative values to our volume, and that's why it doesn't give the actual volume of the solid. Remember, volume, like area, is a number that always, always, always has to be positive. There is no such thing as a negative area. If you still think there's such a thing as a negative area or a negative volume, because integrals can be negative, go back to the very first video where I explain the difference between an integral and the area that you can compute with an integral. Okay, now let's go back. Let's go to our dome-shaped enclosure for insects. So we have here is we have a dome. I won't read the whole problem again, but we have a dome like this, and the dome is really, it's like a solid of it's like a, I'll continue to draw it like this actually. It's like a solid of revolution about the y-axis. I've given you the equation that you can use for that. So we have our dome, and the way this works is that since the bees, they don't really care how far they are to the left or right in the dome, but they do care how far they are from the floor, because the floor is what's covered with insect repellent. What we want to do is in order to ultimately find the number of bees in the dome, as we do in the last part of the problem, we want to do is we want to add up cross sections like this. So we have sort of circular cross sections that are thick in the y direction. So what I'm trying to do is sort of build up through these through the first three parts of the problem. I'm trying to build up the idea that we can calculate what the radius of this circular cross section is, and then what the volume of a slightly thick cross section is, and finally how many bees are in the cross section. So the cross section of the dome parallel. So in part A, we want to know what the radius of the circle is. So this circle has a radius that goes from here out to here, and we know that this equation is x equals the square root of 1 minus y squared. So that's fairly simple. What that means is that every point here is going to have the form square root of 1 minus y squared comma y, and we can easily see that the distance between that point and the y-axis is just given by this expression. So the radius at a height of y is just square root of 1 minus y squared. Now, the volume of a thin cross section, in other words, this is like a circular cross section that has a little bit of thickness in the y direction, that's just going to be pi r squared. This gives the area of a cross section. And then to get its volume, we have to multiply by its thickness. So since we know the function for the radius, that's going to be pi times square root of 1 minus y squared squared dy, or I'd prefer the way you write it is pi 1 minus y squared dy. That would be preference, the preferred way to write it. Okay. And by the way, if you're asking the question, well, which one of these would I want to see on a test, you're asking the wrong question. The issue here is to understand why this is the correct geometry. So I'm gonna leave that to your discretion. In general, we certainly think that you should recognize that the square root of some expression squared is just going to be the expression under the radical sign. Okay, so now with respect to the b's, the enclosure in this problem, describe what quantity the expression 7500 y squared times pi 1 minus y squared dy refers to. Okay, let's do this using the analysis I showed in the density videos. We know that this is going to be, we know that this is going to be the volume of a thin cross section. Volume is measured in cubic meters. We also know that this number here, 7500 y squared, we're told what the significance of that number is. That's the density, the volume density of B's. So this is going to be measured in B's per cubic meter. And we're just multiplying these together, so we sort of expect that this is going to be actually a number of B's. In other words, whatever this number is, it's a number of B's. The question is, where is it the number of B's? Well, this is the volume of a thin cross-section, a thin disk rather, we'll call it that. And this is density, in other words, B's per volume. So the correct answer here is that this is the number of B's in one thin cross-sectional disk. Okay, now finally in part D, what is this integral give? Well, as we can see, we have here this expression from part C. That's the number of B's in one thin cross-sectional disk. So we're adding up a lot of what an integral does, of course, is it adds up these thin cross-sectional disks. Well, which ones does it add up? It's going to add them up from a height of y equals 0.4 up to a height of 1. In other words, the top of the disk. So really, if this is the dome, we'll draw a circular floor there. What we sort of imagine is that that's y equals 0.4, and the top of the dome is y equals 1. So what this really is the number of B's in that part of the top of the dome. In other words, the part of the dome that's either, you can describe it either as going from height of 0.4 all the way up to the top of the dome, or you could say it's within 0.6 meters of the top of the dome. So this is the number of B's within 0.6 meters of the top of the dome. Or you could say from a height of 0.4 up to a height of 1. I don't really care which one of those you say, but that's this is the important concept, is that's what this integral is counting up. Okay. So now it's sort of your turn to figure out how to do one of these. What I gave you before is a problem that really suggested kind of the disk method. This problem where, I see why it's doing that. I'm going to have to work on how to stop that. This problem, what we have for the dome is, it's the same dome, but the insect repellent is here. I'll put this in red for poison. So that's where the insect repellent is. So instead of the bees wanting to stay away from the bottom of the dome, now they want to stay away from the center of the dome. The important point is that it's really one cylinder like this, one cylindrical shell, where all the bees in this shell have the same, the density is the same within that shell, because every point in this shell is the same distance from the pole in the center of the dome. So what you want to do is figure out how many bees are in one shell and then just add them up. We can see that let's first of all find find the radius and height of the shell. So the height of the shell, let's see, this equation is going to be y equals square root of 1 minus x squared. Now, how do you know that it's y equals square root of 1 minus x squared? Well, what I did is I took this circle, this semicircle here, not even the whole semicircle. What I really did was to form this dome, I took this curve and revolved it around the y-axis like that. Well, what is this curve? This curve is just a quarter of the circle, x squared plus y squared equals 1. Okay? In other words, you have to get this from the previous problem that it's just that I took a quarter of the circle of radius 1 and revolved it around the y-axis, but that's the equation for a circle of radius 1 centered at the origin. So solving for y in terms of x, I now get y equals the square root of 1 minus x squared. So if that's the case, then what that means is that this distance is going to be the y value, in other words 1 minus x squared. So the height of the shell is equal to square root of 1 minus x squared. And the radius of the shell is just going to be the distance from the center, from the line x equals 0, out to some arbitrary point x, and that's just going to be x. So the volume of one shell is going to equal 2 pi x square root of 1 minus x squared dx. We know this from the shell method. That's what happens when we add up shells. The integrand, this is what would be the integrand if we were trying to find the volume of this dome. We add up volumes of shells, and this is the volume of one shell. And of course, volume, by the way, is measured in cubic meters, meters cubed. So we're given now a density function in terms of x, which is 7,500 x squared bees per cubic meter. So the number of bees in one shell is equal to 7,500 x squared times 2 pi x square root of 1 minus x squared dx, where this is volume of shell in cubic meters, and this is density given in bees per cubic meter. So the units come out right. In other words, this gives the number of bees in one shell because we take bees per meter cubed times meters cubed. So now to find the total number of bees in the dome, what we know is that this point here is going to be, it's going to be 1, 0, because this is this dome of radius 1. So the largest possible x value is going to be 1, and since we're doing this as the volume of revolution, we can start at 0. Even though the dome extends off in this direction, we took this curve from 0 to 1 and revolved it around this axis to get the full dome. So we're going to do v equals the integral from 0 to 1 of that number that that expression we just found, and once we integrate here, we get 2,000 pi, or 6283.2 approximately. And of course, it doesn't really make sense to have 0.2 bees. So ideally, the answer would be something like 6,283 bees. Although I think we accepted 2,000 pi as the answer. So either way, that's the answer.